Hello, everybody. Welcome to our GSA Northern Territory Division monthly seminar series. This is the last seminar series for the year, and we're finishing right there up on a peak. We've got the amazing Heidi from the Geological Survey of Western Australia and our good geology friend from across the fence coming here to talk to us about Precambrian biostratigraphy. Before we begin, I just want to firstly acknowledge the countries that we're all dialing in from across Australia. I'm up here in Darwin in beautiful Larrakia country, so I want to pay my respects to elders past, present and emerging, and extend that welcome out to any Aboriginal or Torres Strait Islander people who are here today. So welcome. Thank you all for coming. It looks like we're in for a real treat here. Heidi's presentations are always amazing. I haven't prepared any thing for you, Heidi, in terms of an official bio, but I'm not sure you'd like a stuffy bio read out. So Heidi's been in various roles in the Geological Survey of WA. We've had a good relationship as geologists from NT Survey and WA Survey, as well as through Geoscience Australia. Heidi is an extremely collaborative person who loves sharing her geology and her passion for stromatolites in particular and other types of fossils. So I'm sure we're in for a real treat today. And over to you, Heidi.
Oh, thank you, Amber. I had to unmute myself, sorry. Thank you so much for the invitation and that beautiful intro, always lovely. One of my good rock friends there, Amber. Nice for you to intro me. But yeah, thanks to you and Kate for the invitation to talk at your final NT GSA meeting of the year. So those of you who know me will know that I absolutely love the territory. So I love working with my good pals over there at NTGS and Amber, and that some of my favorite rocks and fossils actually come from the NT, even though I'm based over here in WA. So before I begin, I should also acknowledge the traditional custodians of the land on which I'm meeting. That's the Whadjuk Noongar people. I acknowledge their elders past, present and emerging. And yes, so my talk today, just give me the thumbs up, Amber, that I am actually sharing the right screen. You can see that? Yes, cool. So my talk today, I'm hoping to take you on a journey through some of the history of Precambrian paleontology. So a field that has emerged relatively recently when compared with the well-established geoscience discipline of Phanerozoic paleontology. But in navigating this record of ancient life, it's important to not only acknowledge the marvels, but also some of the challenges that come with studying a fossil record that stretches back almost 3.5 billion years. There we go. So to set the stage, I thought it important to touch firstly on what is undoubtedly the elephant in the room, and that is that paleontology is inherently a Phanerozoic-centric specialty of geoscience. So the Phanerozoic, as most of us will know, includes all the rocks that were deposited from about 540 million years ago to the present, as displayed here. So the very name Phanerozoic from our geological timescale actually means visible life. And in fact, the distribution of fossils is what divides the Phanerozoic into its three eras. So each of the three eras relating to the kinds of fossils that you'll find in the rocks of their respective ages. So the Paleozoic, the basal era of the Phanerozoic, derives its name from words meaning ancient life. And that's because the life that you find in the Paleozoic is really quite foreign to the life that we have here today on Earth. So you'll find organisms like trilobites that are extinct today, but you'll also find some things like brachiopods that, if they do exist today, they have limited diversity or are quite rare. The Cenozoic era takes its name from words meaning new life, and that is because it's the time period with fossils that are most like the life today on the planet. And then the Mesozoic, the time when dinosaurs roamed the Earth, takes its name from words simply meaning middle life. As well as dividing the Phanerozoic into eras, fossils across all time periods are used for defining boundaries. So correlating geological units, telling us the age of rocks that enclose them, and even telling us how the rocks were once arranged in paleogeographies. So paleontology, the study of past life, has a rich history, with the earliest recognition of fossils of marine organisms indicating that land was once land was once underwater, dating back thousands of years ago. But the widespread understanding of fossils and their relationship to life of the past really began in the 17th and 18th centuries, with the term paleontology being coined in 1822. Paleontology as a geoscience discipline has seen a tremendous expansion in activity since, but during this early history of paleontology, the discipline was really constrained to fossils from just the Phanerozoic. But as most of you will know, the Phanerozoic is only a small portion of the geological timescale. So what about evidence of life from Earth's other 3 eons? Well, around the time of Charles Darwin's Origin of the Species, the field of Phanerozoic paleontology was already well and truly established. But this was far from the case for Precambrian paleontology. In a world where there was widespread acceptance of evidence of life, ancient life, to be found in rocks that were Phanerozoic in age, the prevailing view was that there was no fossils to be found in rocks that predate the Cambrian. So in this quote here from Charles Darwin's text, he acknowledges that if his theory of evolution was correct, then presumably the Precambrian had to be teeming with life. Yet he states that the fossiliferous rocks of this age had not been found. Now, as someone who works in Precambrian sedimentary basins, I find this really outrageous. Clearly, old Charles didn't spend much time kicking around rocks in Proterozoic basins, as those of you who work in Proterozoic basins will agree that the macroscopic evidence for life there is really hard to miss. But what is even crazier to learn is that this prevailing view that the Precambrian world was devoid of life actually persisted for another 200 years beyond this point in time. So it was not actually until the 1950s that we really see the beginning of the geoscience discipline of Precambrian paleontology. Now, that's not to say that there was not those who attempted to document evidence of life in the Precambrian. So Charles Doolittle Walcott was one such paleontologist who did make claims of the evidence of life in the Precambrian. So Charles was an esteemed and well-respected paleontologist of his time who worked for the US Geological Survey, where he went on to be the director before working the latter part of his career at the Smithsonian. Perhaps his greatest claim to fame was his paleontological work on the soft-bodied fauna of the Burgess Shale. But prior to this, during his time at the US Geological Survey, Walcott worked on geology in and around the Grand Canyon of Arizona. There, he described what he recognized as stromatolites in some of the Precambrian successions. So from a manuscript that he authored in 1899, he says, "When collecting material in the Chua terrain in 1883, I was strongly impressed with their resemblance of the forms occurring in the Upper Cambrian rocks of Saratoga County, New York, which Professor James Hall subsequently described as Cryptozoon proliferum. The mode of occurrence strongly suggests the organic origin of the forms named by Dr. Dawson and partially illustrated on plate 23 of this paper." And I've illustrated here plate 23 of that publication. So there in the rocks of the Chua group, he recognized a stromatolite ridge with features in common with Cryptozoon fossils that had previously been described in Cambrian age rocks and clearly were biogenic features. Charles Walcott had come very close to unlocking the Precambrian fossil record at this earlier point in time, which perhaps would have surpassed even his Burgess Shale legacy had he managed to convince his contemporaries of his find. But Precambrian life's moment in the light in the 1900s was to be rather fleeting. Albert Charles Seward, the Vice-Chancellor of Cambridge University, was at the time the world's leading Phanerozoic paleobotanist. He refuted Charles Walcott's claims of biogenicity of the Chua Precambrian stromatolites, publishing in a textbook in 1931 that Walcott's interpretation of Cryptozoon, the Precambrian stromatolite, is, I venture to think, not justified by the facts. it is clearly impossible to maintain that such bodies are attributable to algal activity. We can hardly expect to find in Precambrian rocks any actual proof of the existence of bacteria. See, the problem with Walcott's discovery of Precambrian fossils was that not only had they been previously unknown, but also that they were far too old to fit the widely accepted view that there was no life to be found in the Precambrian. In modern times, we would probably refer to Albert Charles Seward as reviewer too. But in hindsight now, what we know is that Walcott had actually come very close to throwing wide open the Precambrian fossil record at the turn of the century. Recognizing correctly that Precambrian stromatolites were biogenic structures only to be shut down by Seward's assertion that was biased by the view that there was no life to be found in the Precambrian. And so our record of life being constrained to the Phanerozoic persisted for more than the next 100 years. But in the mid-20th century, that tide began to turn. Advances in geological and paleontological techniques, coupled with a growing appreciation of the importance of the Precambrian, prompted a paradigm shift, and paleontologists finally started to recognize the potential treasures hidden within the ancient rocks predating the Cambrian. So in the 1950s, there were a number of paleontological advances that we can credit with sparking the beginnings of Precambrian paleontology. In fact, many Australian fossil sites have been pivotal in this regard. One site that probably won't need any introduction to this audience is the, of course, amazing Ediacaran Hills of the Flinders Ranges. So in 1946, Reg Sprigg discovered in the Ediacaran Hills of South Australia the remarkable soft-bodied fossils that have gone on to become known as the Ediacaran biota. These fossils were originally thought to be Cambrian in age on the basis of them clearly being fossils and the prevailing thought that at the time there was no life or fossils to be found in the Precambrian. Work in the following decades by Martin Glazner and Mary Wade, however, firmly established that these fossils were in fact from successions that could be correctly assigned as Precambrian in age. For the first time, we had undisputed fossils indicating a rich diversity of life, unlike anything that was previously known to exist in rocks of Precambrian age. There was to follow an academic argument about what to do with these fossils. So should the Precambrian-Cambrian boundary be extended back in time to incorporate these fossils into the Phanerozoic, holding true to the ideal that fossils were not found in the Precambrian, or would common sense prevail? Luckily, sense would prevail, and in 2004, the IUGS declared the first new geological time period in 120 years, with the Ediacaran period being assigned to the uppermost Precambrian. So this firmly established that there was life to be found in the Precambrian after all. But how far did life exist further back in time was still far from established. The next great advance in this regard came with several important microfossil discoveries. Around the same time that paleontologists were documenting the Ediacaran fossils from the Flinders Ranges, in other parts of the world, palaeontologists had started using standard acid processing techniques used to recover palaeonomorphs from Phanerozoic rocks on samples from the Precambrian. Boris Timofeev from Russia was one notable paleontologist who had great success in the recovery of microfloras from Precambrian shales using this technique. Simultaneously, paleontologists began discovering microfossils in chert. Here on the slide is perhaps one of the most well documented of these, the 1.9 billion-year-old gunflint biota, first documented by Stanley Tyler in 1953. So although widely accepted as biogenic today, at the time of discovery, the gunflint biota was largely dismissed on account of the material being far too old and simply unbelievable to be biogenic, perhaps because the forms were most unlike microfossils that are found today. A biogenic origin of these microfossils wasn't really widely accepted until another Australian discovery. The great leap forward came with the discovery of the documentation of the Bitter Springs microfossils, so originally described in 1965 by Bargehorn and Schoff. These microfossils were widely accepted by paleontologists on account of them being only 850 million years old, but also probably in part because they were remarkably comparable to modern microbes and so could not be disputed as anything but biogenic. With the widespread acceptance surrounding the Bitter Springs microfossils, these similarly preserved from the gunflint gained greater credibility, and all of a sudden we now had evidence of life extending well back into the Proterozoic that was no longer disputed. But the true unlocking of the Precambrian record came in 1956 with the discovery of modern stromatolites growing in Hamlin Pool in the area of Shark Bay, located on WA's midwest coast here. Our former GSWA director, Phil Playford, and UWA grad student Brian Logan were the initial discoverers of this site and undertook much of the early work documenting these biogenic structures that are accreted by a community of benthic microbes. The stromatolites at Shark Bay were recognised as analogues for structures that had been detailed in the Precambrian rock record fossil stromatolites. This discovery really paves the way for unlocking the fossil record of life on Earth right back into the Archean. We now know that life on Earth extends back to at least the Paleoarchean, with the oldest widely accepted evidence of life on Earth being from the Dresser Formation, which outcrops in the Pilbara region of WA. Here we have some fossil stromatolites that are 3.48 billion years old. And if we consider that the discipline of Precambrian paleontology only really came into being in the 1950s, that is just over 70 years of time, we have extended the known range of life on Earth from just over 500 million years to sevenfold that number, to just under 3.5 billion years of a fossil history, which is pretty remarkable, I think. Now, given that the biggest application of paleontology in the Phanerozoic is biostratigraphy, it seems obvious that it was a logical progression for paleontologists to start to attempt to apply the same methods in the Precambrian. So much of the early focus of stromatolite research was on biostratigraphy and how Precambrian stromatolites would be used as a correlation tool in regional mapping programs. So this method was first employed in Russian sections with great success. But in Australia, the method was pioneered by 3 paleontologists. Malcolm Walter was one of those, alongside Wolfgang Price and my predecessor from GSWA, Kath Gray. Working together, the 3 of these researchers built an extensive database of stromatolite occurrences across the Centralian and the Adelaide superbasins, and built a scheme that was used for correlation. The basis of this method was by systematically describing stromatolites, the same forms could be found in age-equivalent units. The method was successfully employed in correlating successions of the Neoproterozoic across Australia and forms the basis of correlations that still exist today. So anyone who follows my work here at GSWA will know that this is the bulk of the work that I do on a day-to-day basis. Not just in the Neoproterozoic, but in older Proterozoic basins also. So I'm currently working in the Heidi, Ashburton and Hamersley basins. Basins using these same methods with success. Using stromatolites for regional correlation is recognised as a viable tool at GSWA and routinely employed in our regional mapping and stratigraphic programs. But in addition to stromatolites, there are a number of other Precambrian fossils that have been applied to biostratigraphic schemes with great success. I'm only including a few from in highlights reel here with a somewhat Australian-centric view. So here on this slide, I've included 2 stromatolite images at the top from the Duck Creek Dolomite, a project that I'm currently working on. To the right of these is a reconstruction of the Mesoproterozoic fossil string of beads, or Horodischia. In the second row is the Ediacaran fossil Aremberia bankside. So those of you who came to CABS will know that we are successfully using this as a stratigraphic marker for the Ediacaran in the Centralian superbasin, and it also has occurrences in the Adelaide superbasin. To the right of these, we have some Tonian vase-shaped microfossils, and in the bottom row, I have included some organic walled microfossils and acritarchs. And I, of course, could not prepare a talk on Precambrian biostratigraphy without including the lovely Cerebrosphaera globosa, which used to be known as the Cerebrosphaera bucci, because as those of you who will know Cass, that was probably one of her favorite tools used and employed in many of her biostratigraphic correlations. So as a shout out to Cass, I couldn't prepare this slide without including Cerebrosphaera globosa. But for my talk today, I've chosen just two of these to talk about in detail. The first one is my fossil of the moment that I'm actively working on for our Centralian project. And these are vase-shaped microfossils. So these are microfossils known globally from the latest Tonian succession, globally from latest Tonian successions. These ones I've included on the slide here today are from the Tagari group in Tasmania and were redescribed recently by Leanne Reedman. So vase-shaped microfossils are exactly as the name suggests. They're microfossils that are vase-shaped. They're small teardrop or hemispherical tests with an aperture opening at one end, and they range in length from 20 to 300 microns. Vase-shaped microfossils are the holy grail of Precambrian fossils, as they have the potential to provide biostratigraphic resolution down to a scale that's comparable to that of the Phanerozoic, which in the Precambrian, characterized by long-ranging fossils, is exceptionally rare. Even more exciting is that they are one Precambrian fossil that has actually been suggested as a potential index fossil, again in Precambrian paleontology, almost unheard of. Their biostratigraphic application is enhanced also by the fact that they are found in a variety of preservational modes and that they have a widespread distribution in a variety of rock types. So and also typically where they occur, they are found in great abundance. Now, my title did actually promise to detail not only the good, but also some of the potential pitfalls of Precambrian paleontology. And this was another motivation behind choosing to highlight VSM's vase-shaped microfossils in my talk today, as I think vase-shaped microfossils are quite representative of some of the problems you can encounter in Precambrian paleontology. So one of the pitfalls that comes with working on fossils in the Precambrian is that they are sometimes very simple in morphology. So there is not the complexity that comes with life, later life in the Phanerozoic. So quite often it is not possible to split fossils out and taxonomically assign them as paleontologists would do in younger settings. Vase-shaped microfossils is actually a basket term that is used to assign any microfossil that is vase-shaped. So here on this slide, I've included some Ediacaran vase-shaped microfossils published from the late Ediacaran Denying Formation of South China recently. Now, some of you paying attention to my last few slides might be doing a double take now, as you will realize that I've just said that vase-shaped microfossils are an excellent biostratigraphic marker for the latest Tonian, but here are some vase-shaped microfossils from the Ediacaran. So here we have two vase-shaped microfossils, and certainly in terms of their gross morphology, we can identify these as being morphologically similar, and so it's certainly plausible that they're grouped together underneath the classification of vase-shaped microfossils. They're both hemispherical with an aperture opening at one end, and they contain a test or shell. Except when you are a microfossil, it turns out that size really does matter. So here I am showing these two microfossils at the same scale, and there is an obvious difference immediately apparent. And in fact, these two microfossils have suggested affinities that are very different from each other on the basis of their size. So the Tonian vase-shaped microfossil, by comparison with modern taxa, are most likely a form of testate amoeba, whereas the Ediacaran example from South China is most likely a foraminifera. Now, if we were to simply take at face value the occurrence of vase-shaped microfossils in both Tonian and Ediacaran successions, it would seem that there is maybe not biostratigraphic value to their occurrence. It is only with an approach looking beyond the basket term of vase-shaped microfossils that we can make an application from it. So this kind of data in the Phanerozoic would in all likelihood be abandoned for a better scheme. Here we have another one of my favourite fossils of the moment, the string of beads fossil, Horodischia williamsi. So in the 1990s and early 2000s, GSWA regional mapping programs encountered these string of beads fossils, and geologist Ian Williams and then later David Martin made extensive field collections of these fossils. And Kath Gray, our former state paleontologist, as some of you will know, also worked extensively on this fossil. The beads were identified from more than 50 localities in WA, distributed over a strike length of more than 500 kilometres within the Backdoor and Stag Arrow formations of the Collier Basin. The fossil was used not only as a regional marker for mapping, but also to correlate stratigraphy in which the beads were distributed. Importantly, despite extensive regional mapping that covered the area, Horodischia williamsi has not been found in any other units of the Bangamall supergroup, even where lithology and depositional environments are similar. Now, earlier this year, I was very excited to have identified Horodischia from a North Australian craton locality in the Kimberley, assuming that this most likely implied a Mesoproterozoic age and correlation with units of the Collier Basin. Now, I prepared my abstract to present at PDU3, circulated the abstract to authors, had it ready for submission. The morning I was ready to submit, I opened my inbox to find a new paper alert. Publishing a Tonian occurrence of Horodischia. Tonian? Huh? Not only did the paper document Tonian and Ediacaran examples as Horodischia, but it also had synonymized the West Australian material previously referred to Horodischia williamsi, resulting in what was once a middle Mesoproterozoic taxon with a biostratigraphic application to now belonging in a taxon that ranged from the middle Mesoproterozoic all the way to the upper Neoproterozoic, which would obviously imply little to no biostratigraphic use. Now, this is once again another example of some of the pitfalls of Precambrian paleontology and dealing with fossils of seemingly simple morphology and perhaps very vague affinities. You can see here the amended diagnosis for the genus Horodischia, and I'm confident that any Phanerozoic paleontologist in the audience will undoubtedly be disturbed by the very general nature of this fossil description, as it could really be applied to anything that is a string of spherical structures. You could easily fit any number of unrelated organisms into this description. In fact, this diagnosis could fit things like seaweeds, algae, cyanobacteria, just off the top of my head without giving it too much thought. But this is the nature of dealing with Precambrian fossils. So often their morphology is very simple and there is not diagnostic features that can be used to differentiate what can be widely different organisms. But do I think these fossils are one and the same? Well, I'll be honest and I say I have my doubts. So I think given the constrained distribution of the Mesoproterozoic string of beads, I think that in all likelihood that is an organism unrelated to Tonian and Ediacarans, to the younger occurrences being described from the Tonian and Ediacaran successions of China. I think that whilst they superficially share some features of morphology in common, that there's enough differences to warrant classifying them as different things. So I think one of the things that's been overlooked in the Mesoproterozoic material from WA is the presence of a holdfast attaching the strings to the seafloor, which is so far absent in the younger strings from South China. So here on the right are some field images of Horodischia and some co-occurring sedimentary features that I've included a field picture here of what I would consider holdfasts with strings of beads coming off it. So I do think that in the detail, we may actually be looking at two different organisms with a completely different mode of life. But I also think that there's evidence to suggest that the Neoproterozoic material has a level of complexity that we are not seeing in the Mesoproterozoic material. So here you can see some more plates from the South China material, and you can see organized groupings of beads. So we've got a double line here, and this and this sort of organized grouping of beads is not something that we see in the Mesoproterozoic WA material. I think this is maybe best explained of a case of how simple morphology that is common in many Precambrian fossils can result in the taxonomic lumping of disparate organisms. So these two examples really only just scratch the surface of what are some of the pitfalls of Precambrian paleontology. And really, I don't have time to cover such an enormous topic in a short talk, but I thought it important to acknowledge just a few more. So thinking back to the earlier example I gave of the Phanerozoic paleobotanist Albert Seward dismissing Walcott's discovery of the biogenicity of Precambrian stromatolites, I think it's important to acknowledge that we cannot take a Phanerozoic approach to paleontology and apply it to the Precambrian fossil record. I've included this graphic here to figure how I imagine a Phanerozoic paleontologist might look at Precambrian taxonomy. So it's commonplace when working on Phanerozoic fossils that a classification would include all of these categories and sometimes even additional ones. But in the world of Precambrian paleontology, we're often working in the taxonomic dark. So the majority of Precambrian fossils will sit under a classification of Incertae Cetus, which is a term used for a taxonomic group where its broader relationships are unknown or not defined. Most Precambrian fossils are contentious even at the highest order of whether they represent life or not. This problem is compounded by the comparatively sparse Precambrian fossil record, and the affinity of Precambrian fossils is inherently almost impossible to demonstrate, as it's quite likely that for some of these examples of life, there are just simply no living analogues to be found on Earth today. And I guess to round out on the promise in my title, I should acknowledge that sometimes in the discipline of Precambrian paleontology, with so many unknowns in a world of blobs and splodges for the most part, that things can have the potential to go really pear-shaped. So here on this slide, we have an example of a mistaken identity where the presence of a fossil Dickinsonia was used to reinterpret the age of a geological succession in India to be Ediacaran. After just 3 years of weathering, the fossil was found to be remnants of a decaying beehive. Oh dear. And I guess off the back of that cautionary tale, I'll round out with a few take-home messages. So I hope I've managed to convince you that Precambrian life is an entirely different beast to that of the Phanerozoic. So a Phanerozoic approach should not be taken when working on Precambrian fossils. And also that it's important to acknowledge that Precambrian paleontology is a relatively new discipline of geoscience. It does not have the wealth of history that the field of Phanerozoic paleontology comes with as yet, but is nonetheless an exciting field to work in with lots of promise, including in the area of biostratigraphic application with the right approach. A huge thanks to, I've just got a few acknowledgements. So a huge thanks to my paleo pal in New York, Alex Bartholomew, for the images of the cryptozone locality that he's shared with me. But also I need to acknowledge my Neoproterozoic partner in crime, Peter Haynes, and obviously Kath Gray for the wonderful legacy of her Precambrian paleontology work that she has enthusiastically shared over the decades with me. And I'll open it up to questions, I think. Thank you.
Thanks, Heidi. And I was wondering what your ugly was going to be. So that's hilarious. And definitely a lessons learned, you know, phone a friend if in doubt.
Yes, phone a friend. Yep. Sensational claims require sensational evidence. I think, you know, that's the old adage for working in the Precambrian, and it's really important. I think we have a responsibility to do solid work, and yeah, I think, you know, there's a lot of things that I culled out of this talk because, you know me, I could talk for hours about fossils. But I think a really important message that I took away from being in the field with Jim Gayling one time is that he said, you know, you find something once, that's interesting. You find that shape or repetition again, that's interesting, but you need to keep finding it over and over and over again, and then you have a publication. And that's sort of a solid approach to working in the Precambrian, because a lot of things are just sort of splodges and vague impressions on the rock. So, repetition of your observation is a really important key. So, yeah, I think that Dickinsonia thing was unfortunate, but yeah, you've really got to take a pretty solid approach when looking at things in the Precambrian to avoid mistakes like that.
Absolutely. So I think we're just going to open the floor for any questions. But before we do, I do just want to thank Kate for the amazing work you've done in getting all of our seminar series this year. It's been a lot of work for you throughout the year, wrangling everybody, selecting such an awesome showcase every month. So big thank you to you, Kate.
Thanks, Amber. And thanks to all the speakers, because it is, extra work really that I'm asking them to do. So I'm always very happy when people agree to come and give a talk for us at lunchtime or after work one day. So yeah, thanks. Oh, someone's got their hand up for a question, Amber.
Yeah, over to you, Carrie.
Hi, okay, can you hear me?
Yes.
Oh, I'm a bit scared. I don't usually ask questions here, but I've recently found myself somewhat adrift in the Centralian basins. I'm a Mesozoic palaeontologist, so I've got no idea what I'm looking at here. And the first question I was asked by someone I was advising was, what's the zonation scheme in the Proterozoic? So obviously there's the Cath Gray's work in the Acritarchs, which I'm more familiar with, and some of the stromatolite work, which I've been recently reading. One of the biggest problems I've had is finding out how Cath Gray's work, the stromatolite work, and Zhang's work in like the Warburton and Raui basins, how they tie to each other to help us to sort of, obviously it's a very long period of time and you sort of have to jump between fossil groups to try and find your correlation things. Is there anything in production or anything that's, I haven't been able to find anything that shows how these things all relate to each other than possibly that figure in Cath Gray's book, which kind of starts trying to tie some of these schemes together.
Yeah, that really is the latest update that we'd have, Carrie, but it's a really good point. Sort of, yeah, coming from the Mesozoic and then going down to the Neoproterozoic, we're not as organized. We don't have that stuff together because you're sort of clutching at all these different things that, it's really about building a database. And then I always advocate for a quantitative approach in the stromatolite application. So, it's sort of not as organized as Phanerozoic material in that we sort of just collect data on stuff and think, could this be a correlation tool? Is it a method? And really, if you think about stromatolites and how we use them, well, we're using them for correlation, but does it equate to biostratigraphy as such? Probably not a one-to-one relationship there. But GSWA is certainly working on our component of the Centralian, and we do have 2 publications in the works that, Peter Haynes is pretty busy at the moment doing he's got a lot of balls in the air with being Mr. Hydrogen, Mr. Salt, Mr. WA basins of covering the whole state. But we do have a 2 reports to wind up our Centralian project, the Amadeus component of that. So we've got a stratigraphic report and a biostratigraphic report. So I've got a sort of draft of the biostrat that's waiting for Pete's stratigraphic report to come out first, but I don't know. I mean, it's not promised as a product on the work program for a while, so I'm not sure when that will be released, but that is something that we're working on. And now we're currently working on the Officer Basin as well. So we have some unpublished data there that will sort of come out in survey reports and things. But obviously the NT GS are also working on things. So Charlie might be able to alert you to things that they publish through AGES and their various products. So yeah, I mean, the best thing to do is just sort of contact one of us, and we do have monthly team meetings going at the moment. So we're sort of updating each other across the border on what we're doing, and you'd be welcome to chat with us at one of those maybe if you want some more info. And I'm always happy to talk about the stroms and any of the microfossils that I know about. So I'm working on the Bitter Springs aged microfossils and vase-shaped microfossils, but not really the Acritarchs. But I mean, Kath has a huge database of info, so I don't think there's much I can add to that.
Awesome. Thank you for that information. And yeah, I would be actually
no
keen to
worries.
talk to anybody. Just for background, I'm consulting to Geoscience Australia at the moment, their hydrogeology department, and they're sort of, some of their work is building up their Australia-wide aquifer models. And as part of that, they've sort of got a database, building a database of all data that's, and it's sort of it's mainly a lithostrat correlation. So I'm trying to add some chronostrat into that. So
Cool.
yeah,
Yeah.
so we've got a massive database of all the previous work, and I don't know what to make of it. So,
well, we'd love to collaborate and contribute to that. So yeah, just get in touch. No worries.
Awesome. Thank you very much.
Cool.